Hello, everybody. We've heard a lot of amazing methods today and a lot of incredible applications. But one thing that they all have in common is they have a lot of tunable parameters associated with them. This could mean hyperparameters of a deep learning network, could mean feature transformations you're going to do before you even feed it into a machine learning pipeline. And often tuning these is left to the reader. You kind of have to figure out the best configuration to get the most out of these systems that you've built. So what I'm going to talk to you about today is how you can apply techniques from Bayesian optimization and optimal learning to help you solve these problems. And I'm co-founder and CEO of a company called SIGOPT that does this as a service, but this talk will be mostly about how you can apply these methods and a little bit of intuition behind why they work better than what people tend to do today. So first up, I'll tell you why this is a hard problem. I'll talk about kind of the standard methods, like if you're going to go grab scikit-learn or TensorFlow or something like that, use the open source. A lot of their examples use some pretty standard techniques. I'm going to talk about Bayesian Global Optimization and go through one specific path through the literature about how that problem is solved. I'll talk about how you actually want to compare these. Once you have an optimizer, you want to make sure you're using the right one. And then some real-world examples if there's time. All these slides are available online as well, though. So first up, I'm going to tell you two things you already know. Machine learning is extremely powerful. We've learned about that all day today. But tuning these systems is extremely expensive and non-intuitive. When you look at something like one of these complex machine learning systems, it can be a very difficult problem to solve. So here's a quote from another MLconf veteran, Xavier, who's now the director of engineering at Quora. And in a recent post on Quora, he said that this was actually one of the most difficult unsolved problems of machine learning. Understanding the structure of these DNNs, and then also kind of having a more or less automatic way to tune them. So that's what I'm going to show you today, a more or less automatic way to tune them. So every single machine learning problem has this same structure and difficulty. Whether you're looking at a random forest and trying to select the number of trees, a support vector machine and picking the right kernel, or something like a deep learning system that has a ton of different knobs and levers that affect that overall performance. This is a great visual representation of what I'm talking about. So TensorFlow released this a few months ago. It was on the top of Hacker News for a while. You can tune a DNN in your browser. And it's great, it's fun, you can kind of click around and play with it. But this really just shows how big of an issue this is. Because in this simple 2D binary classification problem, we have the classic Swiss roll data set up here. We're just trying to figure out a surface that differentiates orange versus blue. There's 22 different kind of knobs and levers that you can tune here. And this is completely independent from the knowledge required to understand that data, do that ETL, feed it into the system, get it spun up and running, and then interpreting the outputs. This is literally just trial and error based knob, lever, and tuning. More often than not, though, you're not playing with a graphical interface, though. You're looking at documentation. So this is the innards of Neon, which is Nirvana's deep learning system. So if you go deep enough, you can find the RMS prop package within there. And there's a bunch of these magic numbers that tend to creep up. Sometimes you may be tuning these explicitly, but otherwise you're implicitly trusting these defaults. So we have a decay rate of 0.95, a learning rate of 0.002. These might have been set to make the example run very quickly, but they may not be the best magic numbers for your data set. And when performance matters, then you might need to be able to tweak these in order to get that best possible performance. And when we look a little bit deeper into the actual documentation, and this is true across any framework, we look at the decay rate here, and it doesn't really give you any intuition about how should I turn this up and down based off of my data. It's a decay rate of states. We can maybe intuit that it should be continuous because it's 0.95 here. But once again, as the user, you're left to kind of trial and error-based methods, which is typically how these are applied. So this can feel a lot like you're trying to climb a mountain in the fog. And this holds because every single time you want to try a different configuration, like let's say I told you a specific latitude and longitude and then asked you to go find me the altitude, you'd have to hike up over there and then measure it. But if I told you to try a specific hyperparameter configuration and then asked what's the holdout AUC of this classifier, you might have to spin up a huge cluster, wait several hours, and then get the result. So we want to make sure we have an extremely efficient method to do this, because when it's time-consuming and expensive, we don't necessarily want to use more exhaustive methods. So the standard methods for hyperparameter search, though, kind of leave something to be desired. So once again, if you download something like scikit-learn and you say it's scikit-learn hyperparameter optimization, it's going to point you to methods like, well, first I'm going to show you what we're going to plot this on. Basically, I'm going to take that mountain, throw it into a 3D graph. But what we look at when we look at these open source tools, more often than not, they're going to tell you to do something like grid search or random search, which has become very popular in the deep learning literature lately. James Bergster has a great paper from 2009 saying how random search actually works pretty well and can beat grid search in a lot of different applications. But what these two methods do is it takes a very difficult, time-consuming problem, and then it tries to solve it by exhaustive brute force in the grid search sense, scaling exponentially with the number of parameters that you're tuning, or requires you to do something that is mathematically distasteful, I would say, which is just kind of randomly guess at the problem. You wouldn't climb a mountain by jumping out of an airplane and hoping you land at the peak. You want to be able to leverage historical information to be able to climb that mountain as efficiently as possible. There are other methods that you could apply to this as well. In the completely black box setting, you probably can't use gradient-based methods, but you could maybe approximate them very expensively. Convex methods make assumptions that you're only going to get to a local optima. There's other global optimizers like genetic algorithms, simulated annealing, particle swarm, but they tend to be extremely evaluation intensive. And if every time you want to try a different configuration, it takes more than a minute, you can't necessarily use these methods. So that's where we're going to turn to Bayesian optimization. We want something that can bolt on top, take no derivatives, make no assumptions about the underlying space, and then efficiently find a global optima, trading off exploration, learning more about that underlying space, and exploitation, leveraging that information that was so painstakingly collected in order to drive you to that best configuration. So ideally, this system would just kind of bolt on top of what you've already written, not require you to rip and replace anything you have underneath, but basically just say, I've got a black box, parameters can come in, and some objective function can come out. How do I find the best parameters to maximize that objective? Or multiply it by -1 and then you're minimizing. And that's exactly how these Bayesian optimization methods work. And once again, you can kind of just think of SIGOPT as an ensemble of those methods, but each one of these, and there's many open source alternatives out there, kind of apply this technique. So, how does Bayesian Global Optimization actually work, and what does it actually mean? So here we have my academic family tree defining it, my advisor and my advisor's advisor. So let's say you have a time-consuming and expensive process, like tuning a machine learning problem. How do you collect information about it as efficiently as possible to make as much money as fast as possible? I used to do this at Yelp on the ads team, where I developed Mo, which is an open source kind of version of some of the tools that we use at SIGOPT. And the goal there was A/B tests are expensive. Running over your entire data set is expensive. How do we configure this system, this amazing advertising system that was built over many years, in order to get the most out of it? But this holds for recommendation systems, search engines, algorithmic trading strategies, really any of these complex systems. So slightly more mathematically, I didn't put any math on the actual slides, but I'm happy to pass on references after this. Let's assume that we have some objective function we care about: loss, accuracy, likelihood. And we can tune certain things about it: hyperparameters, feature transformation parameters, architecture parameters, whatever it is. These are the inputs to some function, and we want to maximize that function, evaluating it as few times as possible. There's a very important kind of hidden point here. Picking your objective function is incredibly important. If you have something that's very good at hitting a target, but you aim it at the wrong target, it's going to hit that wrong target extremely well, but it's not going to match up with what you care about as a business. So when you're picking your objective function, you need to remember to do things like cross-validation, regularization, make sure that this tuning actually extends to some holdout that you really care about. But assuming that you've picked the target well, this can be an extremely powerful tool for hitting that. So in the literature, there's many different ways that people tend to solve this problem. A lot of times this is called sequential model-based optimization. Sequential, we're leveraging historical information to decide what to do next. Model-based in the sense that we're building surrogate functions to understand the response surface. And then optimization, because we're going to take those surrogate functions and use that to decide what to do next. So one particular path through that SMBO literature is Gaussian processes and expected improvement. This is how Mo works. This is how another open source package called Spearmint worked. But there's lots of different ways that you can apply these techniques, and there's lots of different methods behind them. So the way that this works is we're going to kind of use the response function surrogate of a Gaussian process, and I'll tell you what that means in a minute and give you some graphs and some intuition. You can just think of this as kind of a stochastic response surface for what we think is going to happen when we try different parameters. Then we're going to try to leverage that information after we fit our Gaussian process to fit the observed data we've seen so far to say, now that I have this idea of what's going to happen if I try different configurations, what's the most intelligent next configuration to try? And then we repeat. So first, what's a Gaussian process? Well, there's two ways to think about this, and I'm going to do the point-wise intuition here first. The point-wise intuition is, let's say we're tuning a single parameter here, the x-axis. We're going to assume the response to that parameter, this objective function that we care about, is going to be distributed like a Gaussian. So at every single point in the parameter space, we can have some underlying Gaussian response that we're expecting to see back. So at the beginning, we have no data. Maybe it's just mean 0, variance 1. But as we start to sample points, we update our Gaussian process. We update the posterior. And basically now, at every single point in the space, we can say, this is the Gaussian that represents what I expect to see. And you can see that the mean goes up near that point we've already sampled. The variance decreases near that known data point. We have more information about that region of the space. And as we sample more and more, we get this better and better understanding of how this parameter is affecting that underlying objective function. And eventually, maybe if we're doing maximization here, we can have a pretty good idea that we found something near the peak. The other way to think about Gaussian processes is we have some system, and we want to try to be able to model that in some way. So at the beginning, any function in the universe could represent the response of that system. So we have a bag, and in that bag is every function in the universe. But as we start to sample points, we can throw away functions that don't make sense anymore. So if I sample a point with no noise, any function that doesn't pass through that point no longer makes any sense. So we throw it out of the bag. What we're effectively doing is building a distribution of functions. And that is the Gaussian process that represents this data we've observed so far. So the mean of the Gaussian process is that most likely function given what we've observed. But other functions could be equally likely in those areas of high variance. So there's the point-wise perspective, and there's the kind of functional perspective. But once again, this is just a great kind of stochastic regression function to model the underlying time-consuming expensive data we've collected. Once we've decided on this surrogate model, and once again, there's a bunch of different ones that are used in libraries like HyperOpt, TP, SMAC. We want to make sure that we don't overfit or underfit, which is like the classic problem when you're doing regression. So these are 3 identical data sets, 3 different Gaussian processes that could represent them. One extremely brittle, one that just kind of passes through the data. You could design a Gaussian process that looks a lot like linear regression. But basically, intuitively, the one in the middle looks pretty good. But what does pretty good mean? That means, given the data we've observed so far, this is the most likely Gaussian process. And we can do that analytically. We can basically say, given what we've observed so far, we can tune the various hyperparameters of the Gaussian process itself to make sure that we're not just kind of chasing turtles all the way down and say, this is the best possible thing to represent this underlying data. Once we have this surrogate model, now we want to actually do optimization. Don't forget, that's why we're actually here to begin with. There's some process underneath all this, and we want to find the highest point. So one way of doing that is, given a surrogate model, we want to apply some acquisition function to it. We want to be able to say, given what I've observed, what's the point that has the highest expected improvement? I want to beat the best thing I've seen so far by the most in expectation. Other acquisition functions could be probability of improvement. I want the best chance of continually improving on previous solutions. Or knowledge gradient, which tries to learn as much as it can about the underlying space. Expected improvement here can be explicitly plotted in this one-dimensional function. Basically what we're looking for is points with high mean and reasonably high variance, because we think there could be something good in there for us to exploit. This seems like a reasonable point to sample next. So we could sample that point. That updates the expected improvement. Basically, there's no more utility in sampling where we know there isn't something good. This is the difference between something like Bayesian optimization and that grid search. We're not going to exhaustively waste time in a valley. We're going to learn about that valley and then ignore it. So we sample to the left. The beginning, once again, is doing a lot of exploration. It's trying to learn about that underlying response surface. And then it can start to exploit information, find these localized optima where it can try to resolve and figure out where that actual peak is. Then it can go back out and explore, and is doing this automatically, making these trade-offs as it goes. Different acquisition functions are going to make different trade-offs, but in aggregate, these methods tend to converge to the global optima. So that's how Bayesian optimization works. It's a graduate course in 5 minutes with no questions. Happy to answer questions after this, but let's just assume that we have an optimizer. We want to see which one's the best to fit on top of my underlying machine learning pipeline. And we care a lot about this at SIGOPT because we need to be able to A/B test our own strategies. Like when we go present work at ICML or NIPS and we come back with a bunch of cool ideas, we want to make sure that we're actually making progress and not overfitting or kind of going off into the weeds and not actually improving our optimizer. So we need some way to evaluate it. And there's an AutoML ICML paper behind this online. But basically, when you're doing optimization, you care about two things. If I'm comparing two optimizers, I want to know which one got me the better value after some fixed number of iterations. So best found, that's what we care about. We might also care about how fast we got there. So if each one of these evaluations is actually time-consuming and expensive, we want to make sure that we can get there in as few evaluations as possible. So the AUC of this best found value over time is a way to kind of capture that information. So in this case, red beats blue because it got to a better value. In this case, red and blue tied after that fixed number of evaluations, but red got there faster. So now we have some way to kind of differentiate two different strategies. We want to throw a whole bunch of different problems at it. So traditionally, when I was publishing papers in my PhD, when you had a great optimization algorithm, you would go and handpick your 3 favorite functions and show you could beat people on those, and then publish a paper. Turns out a lot of optimization research does this kind of technique of hand selecting some different things and then showing that you work in those areas. And that's great if you know those are the types of problems that you're going to be attacking. But for us, we have no idea what we're going to be attacking. We're working with people in a wide variety of fields. So when we're building our own evaluation software, we took the superset of all of these functions that people published on. And we also took a bunch of real-world data sets and said, okay, we want to look at all the different areas where we could possibly care about optimization and then see how well a bunch of different optimizers applied to that. You need to build some infrastructure behind this. A different ICML paper goes into more detail around this. But basically, you want to be able to very quickly test different optimizers, try out different open source packages, et cetera, to be able to iterate quickly. At the end of the day, you get something like this for each one of those 600 functions or whatever it is. You have method A, which is SIGOPT in 2015, versus something like particle swarm optimization here. And the reason why these graphs are a little bit fuzzy is that a lot of these optimizers are stochastic. Random search is an example of this. If you run random search once and then you run it twice, you're going to get different results. So you actually need to run these many times in order to get statistical confidence that you were able to beat some other optimizer in some context. So in this case, this was a three-dimensional Ackley function with some multiplicative noise, and with high statistical confidence, SIGOPT beat particle swarm optimization. But you can look at the pairwise comparison of a bunch of different methods. So in this case, at that very end state, we can look at the spread of SIGOPT versus random search versus grid search, which is actually deterministic, so it's just going to be a pillar. And then apply statistical tests to see which ones do best. Like I said before, there's lots of different ways to be doing this. Global optimization has been popular in the literature for many, many decades. Bayesian optimization has been around for a couple decades now. A lot of different open source, including Mo, which I wrote at Yelp. But we want to be able to track kind of how well we perform against them and how well we compare against each other. So we basically need a way to do an ordering of optimizers given some collection of evaluation functions. This is that initial ICMO paper I was talking about, but basically you can do this hierarchical ranking of what you care about. We want the best optimizer, we want the fastest optimizer, maybe we want the most robust optimizer. There's different things that you can kind of plug in here depending on your particular use case. Then we can do this kind of pairwise ranked ordering of them and figure out which methods perform best across various different classes of functions. So once again, if you know exactly the type of function that you're going to be optimizing for, then there might be an optimizer out there that hits that function exactly. So in this case, actually, Spearmint was incredibly good at finding boundary value optima. It rushes to the boundary and then can resolve those optima very well. Different methods perform better in integer or categorical cases, etc. SIGOPT's goal is to ensemble all of these methods so you don't have to make those trade-offs yourself, but if you dive into the weeds, there might be a great optimizer for you. Once again, SIGOPT tries to wrap all of this. This is just the two-slide pitch of a lot of times when you're administering this was something that the first time I talked at MLconf, I was pitching Mo, which was that open source that I wrote at Yelp. And one thing that I found over the last 2-3 years, whenever it was I actually gave that talk, was a lot of time is spent optimizing these optimizers. And that's very different than the domain expertise required to build your recommendation systems, advertising systems, natural language processing systems. Basically, all of that work that you're doing is orthogonal to, now I have to tune this black box. And now I have to tune this tuner of black boxes. And so the goal of SIGOPT is basically to bolt on top and provide you this easy interface, do it distributed, do it hosted, do it scalable, do it production ready, so that you don't have to care about it in whatever language that you're doing. So I know I didn't leave a lot of time for questions here, but I'd be happy to take any now, or I know there's a break immediately after this. Once again, all of these slides are online. There's a bunch of examples as well on GitHub, a bunch of deeper examples on deep neural networks, text classification, live demos. It's free for students, free trial if you want to give it a try right now, and we're hiring. So thank you all.